Okay, so let's get right into it. So because we recognize, hopefully we recognize, the initial rate, average rate, instantaneous rate, they're okay, but they're not perfect because once again, they're not going to be constant throughout the entire reaction. What we need is a rate constant. So we use the lowercase letter k for the rate constant. Don't get that confused with equilibrium, right? Big K is equilibrium. Little k is rate constant. And sometimes I really exaggerate how I draw my k's just so we can recognize that the big K is equilibrium and the little k is a rate constant. So this is a proportionality constant that relates the rate of reaction to the concentration of reactants, and it is indeed constant throughout the entire reaction. So in order to use a rate constant, we actually need something that's called a rate law, which is an equation that defines the experimentally determined relationship between reaction concentrations and the rate of a reaction. So within our rate law, we will have the rate constant. And finally, within our rate law, we need to have something called a reaction order. And this is an experimentally determined number defining the mathematical dependence on the reaction rate of the concentration of a reactant. Typically, this is a whole number integer. It can be 0, 1, 2, 3, etc. Okay? So let's see how all of this gets put together. So in kinetics, for one, it's all about the reactants. So let's write that down. It's all about the reactants. And the reason for that is because, as you might have noticed, there was several things where it said experimentally determined, right? Experimentally determined relationship, experimentally determined number. So kinetics is something that's extremely difficult to do theoretically. It is an experimental science, which is why I love it, because I love being in the lab and I like doing experiments. And because it's an experimental effect, when you think about it, if we have a reaction, we typically only have reactants when we start. So we kind of base our kinetics on the reactants. So it's all about the reactants. So for example, suppose we have this generic reaction. A plus B goes to C. Okay? This is how we start to write a rate law. And yes, you have to be able to come up with rate laws in this class. So a first simple way we can do it is just to say rate equals. And it's always going to be rate equals K. Rate equals the rate constant times the concentration of reactants. So, right, that's molarity because it's in the brackets. And it's just the reactants. And we say reactant 1 times reactant 2. So A times B. And we also have to raise those to some power, which is our reaction order. Okay? And it's very difficult for us to just look at a reaction and know what the reaction order is. And we're going to talk more and more about that soon. Okay? So now if I wanted to fill out this in a little bit more specific way, here's where I could use those relative rates that we just talked about. So for example, if I look at this in terms of A, I could say negative delta A divided by delta T, and that's going to equal K times A times B, raised to their respective powers, which we don't know what those are yet, but they will be some whole number like 1, 2, etc. It can be 0 as well. We can see that B has the same stoichiometry, negative delta B divided by delta T, and that equals the same thing. And then we can see that because it's a coefficient of 1 for C, as well as B and A, all we do is change the sign. So now that's delta C divided by delta T equals this rate law. Okay. So let's look at a specific example. So here's the reaction of 2 and O2 makes 2 NOs plus O2. So we could start very generically and say rate equals K times the reactants. Notice we don't even care about the products here because it's all about the reactants. and then we raise it to this reaction order power. Now, it might be tempting at first to look at this 2 right here and say, oh, well, just like in equilibrium, when we had a coefficient in front of something, we raised it to that power. Unfortunately, we can't do that in kinetics. We can do that in equilibrium, but we can't in kinetics, okay? And hopefully that'll become more obvious as we build up this material. And so once again, filling in this specifically, there should actually be a delta right here. So rate equals negative delta NO2 divided by delta T, which is K NO2 times N. We don't know what N is. We got to figure it out, all right? So here's another example that I'm going to show you with real data. And this is an example of how we could figure out what the reaction order is, okay? So for example, in this reaction, here's the decomposition of N2O5. And you can see it's all balanced out with its stoichiometry. And if we were to do this, very careful experiment where we measure the concentration of N2O5 over time, then you can see here we've got 2 instantaneous rates determined at their various time intervals, right? So we can see here when the concentration of N2O5 was 0.9 molar, and that 0.9 molar comes from right here. So hopefully you can see that's 0.90. So if we take the slope of that, someone already did that for us. And so we can see that that turns out to be 5.4 times 10 to the minus 4. That would be molarity per second, right? So that's the same as saying big M per second. But now, if we look later on in the reaction, when the concentration of N2O5 was 0.45, so I'll just highlight that right there. So hopefully you can see off the graph, right, that would be 0.45, take my word on it. So then we get another instantaneous rate, okay? Well, if we think about this for a minute and start kind of looking at these numbers, when I went from 0.9 to 0.45, the concentration went down by half, okay? Hopefully you can see that in your head, right? If I take 0.9 and I divide it by 0.45, let's see, 0.9 divided by 0.45, I get 2. So it decreased by half. Well, what happened to those rates, okay? Well, that's 5.4 times 10 to the minus 4, and I could divide that by 2.7 times 10 to the minus 4, and it's also 2, okay? And you might have been able to see that in your head, right? So what's important to note here, when the concentration is halved, the rate is halved. And this is just for this specific example, right? Each reaction will have a different trend. But here's what's important to note here. Because in this data we saw that when the reaction was halved, the rate was halved, it has to be what we call a first order reaction. So in other words, that reaction order has to be a 1, because if you look at now the way that this equation goes, here we have the rate of N2O5 equals K times N2O5. We notice now here, when this goes down by half, when the rate goes down by half, the concentration went down by half. So that means that had to have been raised to the first power, okay? If let's suppose when the rate went down by a half, but the concentration went down by 1/4, it would be a second order reaction. Hopefully that makes sense, okay? So this is basically algebra, kind of seeing how these concentration profiles evolve and what the order must be. So what is this reaction order business, okay? So here's an example of another type of reaction, and this is NO plus O3 makes NO2 plus O2. And if we wanted to start to come up with the rate law of this reaction, we could first say rate equals K. It's always going to be rate equals K. And then we've got to multiply it by the concentration of reactants, and I'm going to raise it to some power that we don't know yet, right? So raised to the power X, raised to the power Y. Well, as it turns out, this reaction has already been studied, and it turns out that it's first order in NO and first order in O3. That means that it is second order overall. And I get that just by adding 1 plus 1 is 2. So what does it mean to be first order in one reactant and first order in another reactant? Well, if you think about it, if we look at here the collisions, okay, if I have one single NO and one single O3 and they collide, okay, that's 1 and 1 equals 1 collision. But now what if I have two NO2s and one O3? Well, I could possibly get 2 collisions out of that, right? One of these NOs could collide with an ozone, but another NO could collide with an ozone. And we should recognize at this point that in order for a reaction to happen, the molecules actually have to come into contact with each other. Well, now, what if there was 2 and 2 of each? Well, if there was 2 NOs and 2 ozones, we can see that now that leads to 4 possible collisions. And if we had 3 and 3, that leads to 9 possible collisions. And if we had 4 and 4, that leads to 16 possible collisions. So that's where we see this second order overall, because if we increase the number of reactants by 2, it squares the number of collisions. Hopefully you can see that with this example, right? When I had 2 reactants, 2 of each, I got 4 collisions. When I had 3 of each reactant, I got 9 collisions. If I had 4 of each reactant, I'd get 16 collisions. So that's what this reaction order is all about. It's all about relating how when we change the concentration of a reactant, we see a different rate of reaction evolve. And that rate of reaction is all about how often these collisions are happening. Okay? So what gives a reaction its order? So determining a reaction order experimentally requires examining the rate data. That's just like what we did here. We have to examine the rate data, and I'm going to go through an organized way to do that. Determining a reaction order theoretically requires a detailed examination of its mechanism. That is really hard. And we are going to do it. We're going to talk about that at the end, just as an introduction. Okay? But for chemists like myself that do this kind of stuff professionally, it's still very difficult to just look at a reaction and guess what is its reaction order going to be. Okay? That is hard.